was your weekend?
Good. How about yours?
Pretty good.
Did you go to the Pear Blossom Festival or anything?
I was in it. I was
Oh, nice.
representing the school.
Oh, awesome. RCC or?
Mm-hmm.
Oh, that's cool. Are you involved in like ASG or anything? Or?
So I was involved in ASG, but right now I'm the student assistant for the music department.
Oh, nice.
So I was going and getting some hours in.
Oh, cool.
We're on chapter 3 now?
Oh, well, we're still going to be doing chapter 2 today. Morning. Or afternoon. so hopefully you're thinking about this problem. So we'll go over this in a second, just a few announcements real quick. So of course, grab a copy of the lab, and like I mentioned, this week's lab, we're doing a flame test. So please definitely wear your pants this week, and then preferably cotton clothing, so just like a regular t-shirt, right? Check the label, make sure that it's at least close to 100% cotton. That would be my suggestion. All right, so take another minute or so for our warm-up. So trying to write the electron configuration and the Lewis dot structure for chlorine. I did get some, but I don't have some on me. It's not in an accessible spot. All right, do we have thoughts for either one of these? Do we have electron configuration by any chance? You want to go for it? So that looks good to me. Everybody got that? We're getting there. And so this looks good. Let's just kind of recap for everybody's sake. And so again, right, your periodic table should hopefully be looking like this. It should be annotated. And so yes, this should be annotated with 3P. So that looks good. 1, 2, 3, 4, 5. So excellent. All right, so that looks good. And then let's draw. So what's its what's its Lewis dot structure now? And maybe with that, right, how many valence electrons do we have in our electron configuration? So 7, so good. Okay, sounds like we remembered something, that's good. So we have 7 valence electrons. And then, again, I just like to draw this and think about it so we can fill in the electrons properly. So 1, 2, 3, 4, 5, 6, 7. So then our Lewis dot structure looks pretty similar with 7 dots around it. All right, questions on that so far? So this is where we kind of left off last week. So we need to finish up chapter 2, which is fine. I knew we would move slowly because we're doing a little bit of electron dot. We're trying to introduce this. We're kind of throwing a lot right now, which is good. And then we'll be able to kind of move a little faster with 3, but 3 is still dense. So, okay, let's go back to where we were. So we were filling in our periodic table. So yes, we had done this 3p here. Then we said this was 4s. And then this is kind of where we left off. So things start to get a little weird here. So I want to look at some stuff. And then we start, and again, put a big fat star here. So, okay, this is still 3D. We don't want to skip it. And we left off, right, there were 10 electrons total in our d orbitals, 5 d orbitals. Let's just kind of refresh that. Again, I don't expect you to draw them. We just need to know that there are 5 of them, each holding 2 electrons, okay? So far, so good. And so now let's look at the electron configuration of, let's start with vanadium for a second. And let me just try to find a good place to continue our notes here. I'll do it on page 6. So we'll do Monday. And so let's look at vanadium and its electron configuration. And then, so like I may have mentioned, we're not going to do Lewis dot structures of transition metals. I'm just not going to ask that. We're not going to worry about that. But we should at least kind of know the electron configuration. And so again, going back to our notes, we can start at argon, right? Previous noble gas. So now we're at argon. And again, make sure it's labeled. So 4s2, and then 3d, 1, 2, 3. And so that checks out. Oh, just to, again, right, help you study at home. P table, electrons, we can check it. So we click vanadium, and then we find, okay, that matches, right, argon 4s2, 3d3. So now let's look at chromium for a second. And we can just write out, let's just try its expected electron configuration. So it's right next door, oops. It's right next door to vanadium. So what do you expect it would be? Just go ahead and write it out. And so what do we think the electron configuration is? What do we just expect? So argon 4s2, 3d4. And so this is, I'm going to say, first of all, this is a perfectly acceptable answer for our purposes. But I still want you to appreciate the exception and kind of why it occurs, and yeah, understand these scenarios. All right, so if we look at chromium on our P table, so right, we're trying to check ourselves, and then we find, oh, it is actually 4s1, 3d5. And so this may seem unexpected, But again, right, we can understand this actually. And so let's kind of think about what happened. So let's draw out our orbitals. And so the issue kind of arises from the fact that, again, they're very close in energy level to begin with. So we have our 4s and our 3d. So they're pretty close in energy. And so now I'm going to kind of do the expected one, right? If we're just filling it in normally. So we have 1, 2, and then 1, 2, 3, 4. So that represents, right, what we originally thought. And so now you can see where there might be some room to play, again, energetically. Because remember, we're paying a price to pair here. So energy price for that pairing. So then it's actually energetically favorable, right, to put this one in its own separate orbital then. And that makes the d orbitals happy too, that it has one electron in each one. And so, okay, that's why it gives rise to the actual electron configuration. And again, this would be for the ground state. And so now you can already kind of get a taste of why inorganic chemistry is a whole separate field, because we're just talking about it very basically. We're not looking at it in a structure where these orbitals can start taking different energy levels. And so that's where the complication occurs. So again, you want to appreciate it. And then perhaps on an exam, so like I said, if I just straight up asked you what's the electron configuration of chromium, I would accept both of these answers. So if you remembered that this was one of the weird exceptions, great. If not, right, I don't expect you to remember that. You're only 100 level students, like that's perfectly fine. This is a good understanding. But the other thing that I might ask you on an exam is I might lay it out, right? I might say, okay, this is what you kind of expect if you fill it normally. However, we find that the electron configuration is actually this. And that's where you want to draw a little diagram like this and kind of be able to explain that. It's like, okay, these are actually really close in energy level, so that's why it was more favorable to just have one in each separate orbital versus pairing that 4s. All right, so let's keep going. Actually, we'll look at more kind of oddities. So we can look at P table. That will help us move a little faster. So notice manganese doesn't have that weird trend. So now, of course, it has enough d electrons to put one in each. So the s ones are paired. Iron is normal, cobalt is normal, nickel fills normally. And then copper, notice, right, you have, again, another exception where it's just more favorable, apparently, to pair the d orbitals, again, right, some sort of energetic favorability. And then it leaves one lone one in the 4s. So again, I don't expect you to remember that, but if it comes up or you're seeing it now, right, just understand it's from those energy levels being so close. And then zinc is normal. So now we're back over at 4p. So I think we did that. So label that on your periodic table. So 4p, again, following our same trend, right? Same Lewis dot structure as we go across, right? So gallium, germanium, arsenic, krypton, of course. So fills up. Now we're back at the 5s. So 5s1, 5s2, of course. And then yttrium, again, label that 4d. So now we're back to 4d. Then filling in our d's. And then back to 5p. So again, I would label that so you can remember that 5p starts back up. Then we finish up 5p with xenon. So then we go from 5p to 6s. So cesium starts 6s. And so then this is where things can get a little funny, and you have a few discrepancies. And again, you find different explanations. And so I'll explain kind of one way. And again, if you see discrepancies, that could be kind of why. And so let's analyze what we're about to look at. And so we're trying to figure out how to fit in our F block here. And I should have pulled up, let's look up expanded periodic table. And so I'm trying to show it in this form. Oh, come on. Why can't I just see this picture? Seriously, what is going on? Okay, so this is what we're trying to add in here. Golly, every image is behind so many firewalls now. And so they have it set up, I think, what's supposed to be more kind of properly, but property-wise and electron configuration-wise, it doesn't work as well. But what I'm trying to say is, okay, we need to squeeze in our F block. That's down here. So, of course, it's at the bottom of the periodic table to save printer space, essentially. And so let's look at our F block before we start counting and numbering. And so kind of the key thing that I'm trying to set up for y'all is, okay, well, there are 7 F orbitals. They're going to hold 2 electrons each. So how many wide should our F block be? So 14. And so this is where you first have to check your periodic table that you're using, because again, there are some discrepancies. And so if we start with this one and we count across, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Well, that doesn't quite work. And so what I like to do, and I believe that periodic table in the back kind of has it marked, is lanthanide starts over here. And so when we fill up our electron configuration for lanthanum, this is 5D1. So maybe you want to like put 5D1 here, and then of course actinium later, right, is going to be 6D1. And then cerium starts off the F block. So now I'm trying to highlight it, that the F block, right, is really here. So then cerium starts 4F1. And again, right, there might be discrepancies, so let's kind of check p-table, because this should be backed up by some sort of data. And so it agrees with our filling, right? So again, look at lanthanum, and it's helpful to pay attention to the atomic numbers at this point because it gets kind of confusing. So, okay, we were at 56 for barium, right? 6s2. We can see that in our electron configuration. And then, okay, we go over to our, so this is still, again, D block. So this is 5D1. But then instead of continuing with the D block, cerium starts 4F1. Does that make sense? So again, just make sure that's marked. So that's a little confusing. And then we'll fill up again, like normal, like we expect. But again, there could be some exceptions. So cerium fills how we expect. And then as we keep going, so if you look over at element 59, pre-sodium, so notice that one does skip, right, the 5D1. So there are some, right, oddities. I don't expect you to get it all right. Again, it goes back to what do we kind of expect. So let's go through it together. So element 59, pre-sodium, right, electron configuration. Again, this is what our expected answer is. And again, let's just fill it up normally. Look at our numbers. So this is where people always get confused. Which noble gas do I use, right? So use the numbers. So we're at 59. So that means we have to start at the previous one. So xenon. Okay, so then we're at xenon. And then this is where the labeling is so important, right? So xenon, and then just what we expect. So 6s2. 5D1, right, because we have to hit this first, lanthanum, 5D1, and then 4F1, 2. And again, right, what makes it a perfectly acceptable answer is also the total electrons. So xenon's 54, 55, 56, 57, 58, 59. So right, correct number of total electrons. And that's fine that, again, the actual answer actually skips the 5D. But in this case, right, that's not that intuitive. And again, right, those energy levels are so close in energy that this type of stuff happens. And it's also going to depend on, like, its behavior. So that's what kind of dictates its oxidation state. So in reality, this element is kind of acting as a 3+ ion is what it's kind of saying, because it has 3 electrons in the F. And I think I mentioned it that these elements aren't necessarily that exciting because, right, these just kind of turn into valence electrons on the F orbitals, and they don't really do anything crazy like you might hope, but again, not expected to know this. And so then we can check out p-table. Again, just appreciate the oddities. So for some reason at 64, they throw back in 5d7. You can kind of see how that would make sense if you have, right, 7 electrons in each F, or yeah, 7 total electrons in your F orbital, right? So 1 in each one, and then kick the extra 1 to the D. Again, right, I don't expect you to know this, so putting, well, we would get that filling how we expect, but again, little discrepancies are okay as long as you have the total number of electrons. And then we continue to fill it up. And so this is also what I mean. We won't get into the arguments of it right now. So I think officially, at least characteristic-wise, luteum and lawrencium fit better under the D block, but electron configuration-wise, notice that you filled up the entire F orbital on luteum. So there's debate again, right? You can look into the literature and kind of see how people are trying to debate this, classify this. But again, electron configuration is what we expect. So 5d1, 4f14 there. So this is kind of the end there of our F block officially. So 4f14. 5F14. And so again, numerically, once we're at luteum and we finish this, 71, now we're back at hafnium, and then we continue, right? So 5D2. So just remember that you're going back and filling up the rest of the 5Ds. So then 4F14, 5D3, etc. And so you can see that. So hafnium is about what you expect. Again, most students just kind of forget the F orbitals, so don't forget them, right? Again, look at your total electron count. And then these fill mostly normally how we've seen. So just filling in our D block. And then of course, now we're at thallium, now we're at 6p. And again, I would label that on your periodic table 6p, so you don't forget. It gets really confusing at the end. So 6p, finished off that, so we're at 86 for radon. Now we're towards the end here, so 7s, 7s2, and then right after 7s2, we go back to 61 for actinium. And then if you need to write, so this is 5F1 for thorium. Finish up with 5F14, back. So now this is 62. So continue. And again, right, these are pretty synthetic elements anyways, but we should still know how to do their electron configuration. So again, they're filling up normally, like we expect, 5D6, 6D10, and then last, certainly not least, right? Again, I mentioned they're trying to find new elements literally right now, so this could, in theory, continue, but for right now, this ends at 7p here, with element 118, of course, being the official noble gas configuration. Again, obviously, all these are short-lived, radioactive. So again, write that down, our 7p there. Okay, questions about electron configuration. And then we just want to finish up the last bit of chapter 2 is periodic trends. So we'll just kind of recap. Some of it is recapping what we just went over, essentially. And we have our periodic trends. And again, you can squeeze this on your periodic table or maybe make a tiny one with a key. So periodic trends. So some of it we could talk about its metallic character. I'm personally not going to write that one down, but notice, right, it tends to be more metallic or metal character on the left side and then non-metals on the right. And so then we also want to look at size. So size, we have that our radius. So our radius increases as we go down. And then it decreases as we go across. Let me make that a little more clear. So radius, sometimes I like to just write a trend of radius size across, that this is the largest. But let's look at that a little bit more deeply. So radius, again, right, it increases. And so why does it increase as we go down the periodic table? kind of, what do we remember? We can think simply too about this one. Yeah, some more energy levels, right? So we're literally adding just more onion rings. So more, however you want to describe that, right? Either our energy levels, kind of onion ring analogy. Okay, so it's obviously getting further. But then what's kind of strange, and we can think about this, is why does it actually decrease as we go across the periodic table? But protons are always increasing, but think deeply about kind of the orbitals. So where are those electrons being added? We can do a thought experiment, right? Let's compare boron versus fluorine for a second. So, right, they're both on the 2p. So boron has 1 electron in our p orbital, and then F has 7 total valence. So what's going on as we add these electrons here? What kind of happens? Why would our radius shrink? So are we adding any energy levels as we go across? I didn't add any, right? I still have 2s, 2p, 2s, 2p. I just put more electrons in there. And so the explanation is, right, since you're adding more electrons at essentially the same radius, your effective nuclear charge gets stronger. And so kind of the rough way to think about it, without getting into all the effective nuclear charge, is, right, you have 1 electron at this set radius versus now 5. And so now you have more kind of electrons, again, at that same radius, so you can pull closer to the nucleus, right? And so again, right, nucleus always has your positive charge. So if we have more at the same radius, it can contract. So that's why fluorine has a very small radius. Of course, neon would have an even smaller one, right, with all 8 filled up. And so that's where we get the size. And so with that, there's also other trends. And so it kind of follows similarly. So now we have ionization energy. And so let's define this. And so formally, ionization energy is, well, how much energy it takes to ionize and eject an electron. So you have some sort of, and I just abbreviate any atom with metal. It could be, again, any atom, doesn't have to be a metal. And then you add ionization energy to it. And it kicks off an electron, so how favorable this process is. And so what we find is that ionization energy increases across the periodic table. Again, this relates back to just what we talked about, right? So we said if it has a higher effective nuclear charge as it goes across, it's going to be harder to kick off, not to mention, and this is, again, kind of why the octet rule exists, but, right, if it's getting there close to fulfilling the octet rule, obviously, right, they're full, they're complete, high effective nuclear charge, so that's not favorable. versus, and again, right, where we saw a taste of that in our demo, versus if we're starting on this side of the periodic table, obviously, right, lithium gives up an electron pretty readily. It's probably happy to be ionized, right? That also brings it back to its helium noble gas electron configuration. And then beryllium, right, we'll find out it does give out 2 electrons, but like we kind of mentioned, these alkaline earths aren't as reactive. So yes, they give out electrons, just not as readily. And then, of course, ionization energy decreases as we go down. Again, that makes sense, right? You have your onion rings. You can think about how reactive those alkali metals get. So, right, they're happy to give away their electron. It's far away anyway, so lower effective nuclear charge. And then last, well, we'll do kind of last 2 because they go together. So we have this electron affinity / electronegativity. So have people heard of electronegativity at least? Yeah, most people have heard of that one. And so let's make the distinction between the two. So electronegativity measures basically the pull, we'll say, of an atom in a bond. And so that's the key distinction here, is electronegativity is measured in a bond, so it's comparing it when it's in its bonding state, versus electron affinity, where this is actually a different measurement. And so electron affinity formally is just what is the energy either released or required to add an electron. So how favorable is that process? And basically, what we need to know is that our electron negativity increases as we go across / affinity. So they track the same, which is what I like to mention them. And then decreases as it goes down. Again, right, for all kind of the similar reasons, going back to the orbitals, right? So you're seeing how these orbitals are really driving all these trends. And so the only difference, this is again kind of an aside, is so fluorine is the most electronegative element. But then chlorine has the highest electron affinity. And so that's probably not too important for our class purposes. We could get into this slightly the size argument. So the only reason why chlorine has a slightly higher electron affinity is because it's slightly larger, so large things are better at stabilizing a negative charge formally, versus, right, the electronegativity is in a bond, so fluorine is kind of pulling more in a bond situation. So again, that's why there's that slight discrepancy, but otherwise it tracks the same. So just remember, right, fluorine is your most electronegative element. All right, I think that's a good summary of chapter 2 there. Any last thoughts, questions? We can, of course, always go back and practice more electron configuration. But at this point, right, you want to make sure that you have everything annotated and that you could, probably at least attempt this, right, again, based off of your annotations. Feeling okay? All right, let's take an early break just so we can kind of reset for chapter 3 then. So we'll take a 10-minute break, so be back at like 1:50-ish. I'll pull up the chapter 3 notes, so we'll start with our ionic compounds then. And then make sure you grab a copy of the lab too. Yeah. Did you want to just do it after class?
Yeah, I can do that.
Okay, here, I'll just, let me give it to you now. If you want to start on it. Yeah.
Okay.
Otherwise, it's finished with after class.
Okay, thank you.
Perfect. All right, so let's continue as long as we're ready. Although I was just looking at the homework, so maybe we should talk about this one exception real quick. So this is back, chapter 2 homework. So if you already turned it in, that's fine. So, right, I just grade your homework for completion. I may make some notes on it if I, notice wrong answers, but otherwise, you should check the key if you're unsure. But there's actually a weird problem in the homework, and I've just kind of left it because it's a good chance to talk about this. And so it's number 12, it says nitrogen and oxygen. So which is the larger radius, and then which has the higher ionization energy? And so let's go through this one. So we just did the periodic trend one. So which one do we expect to have a larger radius? So we can look at them on the periodic table. They're right next to each other. So which has the largest radius just by trend? Check the trend. Remember, it decreases as we go across, right, filling. So which one's the larger one?
Oxygen is a higher ionization chemical.
But which one's the larger radius? Let's start.
Oh, radius. Is the nitrogen.
Yeah, so nitrogen should have the larger radius. And then what do we kind of expect for the ionization energy? Who is the larger ionization energy? So which one? So we do expect oxygen. And so I'll say that. So we expect oxygen to have lower ionization energy. And so this is actually one of the weird exceptions. And so before, again, let's understand it because there's reasons for these weird exceptions. And so we find that actually nitrogen has the lower nitrogen, has the lower ionization energy, which is unexpected. And so if we look at that, so nitrogen, so it goes back to our electrons. And so again, right, let's think about ionization energy, what we're saying. So we're saying, okay, what is more favorable? Oh, I think I did this. We expect oxygen to have the higher ionization energy, sorry. So expect. And so, right, again, think about what is happening. So ionization, you're asking to lose an electron. But what do you notice about nitrogen and oxygen? And kind of maybe other things we've talked about. What's different?
The atomic mass?
So don't look at atomic mass. What do you notice just like in their electrons? And we've talked about an issue.
Can you talk about the valency?
Yeah, so what do you notice about their valence electrons? But then maybe like the pairing. What do we say about pairing electrons?
What do you mean with that?
Just that, like what happens when you pair an electron? Because we mentioned it caused some issues earlier, right, in the electron configuration where things would kind of move around, but why was that? And it's the same reason why it doesn't follow our trend here. Yeah, so it's the pairing price. And so it's a really odd situation here, right? So yes, oxygen has more electrons, right? We expect it to have this higher ionization energy because of the nuclear charge. But we've also paid this energy price. And so oxygen is actually happier to get rid of its electron because now it doesn't have to pay this penalty for pairing. And so now you're kind of thinking about the neutral versus what's going to happen to ionize. So then oxygen plus, now we don't have that paired electron, so now it's kind of happy about that. Versus nitrogen plus is actually going to have a slightly higher ionization energy because it has, right, all of them filled, so it's kind of unhappy to then lose that one and now just have, right, this empty p orbital. And so again, that's kind of an exception. If I ask you that on an exam, it would be, right, this scenario, why, and I would ask you to explain why nitrogen actually has the higher ionization energy, so I probably wouldn't ask you just like trivia. I'd give you a hint that this is an exception. So that was weird. So nitrogen, actually higher ionization energy, and so again, right, this breaks the trend. All right, so we'll move on for now. And so now let's focus on our ionic compounds. And so now we're just kind of setting up the scene here. And so now we're saying, okay, chemical compounds are composed of atoms held together by chemical bonds. And so now our goal with the next two chapters is really to find these chemical bonds. So what does it mean? And so overall, right, we can just say that there are attractions between these charged particles. And so we have three basic types of chemical bonds. So we're going to have ionic compounds, which we're going to see in just a second are salts. So they're made up of cations and anions. And again, we'll look into that. And then we have our covalent compound. So that is actually sharing of electrons. So we'll see that the ionic is a transfer, so I'll add that too, that involves a transfer of electrons. And then we really won't get into metallic bonding in this class. That is often just classified as a sea of electrons and has to do with the delocalization. But again, we don't want to get into that right now in this class. And so now, again, we want to understand the distinction between ionic versus covalent bonds. So ionic bonds, we can think about table salt. And so notice we have our basic formula unit. They're in a 1-to-1 ratio of sodium to chloride. Again, we'll look at how we derive that in just a second. But I want you to appreciate, so it's not just one unit of sodium and chloride, right? The distinction of an ionic compound is it has this crystal lattice structure here, and it repeats, right, in this obviously ongoing repeating unit. And then you can also think about how this would translate to those physical characteristics. So think about salt. I don't know if some of you ever use like the bigger salt, like bigger chunks that you have to grind. So you can kind of think about what it looks like, very crystalline. And then very hard to break, right? Like you wouldn't really try to slice a grain of salt, but if you were, it would kind of shatter, fly everywhere. So very brittle. So you're starting to see that's where the properties come from. And then covalent compounds, they tend to be lower boiling, we would say. So a lot of them exist as liquids like water or many organic compounds, pentane. Many of your like drugs would be lower boiling compounds, aspirin, all those household compounds you have. And again, they're held together by sharing. And I'll draw it now, but we don't want to get too into it right this moment. So again, oxygen donating 1 electron, hydrogen donating 1, they're sharing. But again, we'll look at that. All right, so let's focus back on our ionic compounds, since that's our chapter. And so I think we had kind of talked about this briefly in lab, again, thinking back to our demo and how does our sodium metal and how does chlorine become tasty sodium chloride. And so an ionic bond occurs between our metal and our nonmetal formally. Again, sodium would be considered our metal, right? Nonmetal be chlorine. You can think about those in their elemental form and their properties. And so it involves a transfer of electrons. And so we'll see this. So our metal becomes our cation, and our nonmetal becomes our anion. And so let's just start off with, see if you can give me either the electron configuration or the Lewis dot structure. We want it of both sodium and chlorine, and then we'll look at the reaction. So what do we get for our electron configuration of sodium? You can give me abbreviated too. So neon, and then what was the last one? Sorry. 3. Yeah, 3s1. And so 3s1, we can clearly see one valence electron, and hopefully your dot reflected that, so just the little sodium dot. And again, chlorine, so what's its electron configuration? So neon, 3s2, 3p5. Does that sound good to everybody? And then again, right, Lewis dot structure should reflect that. Something with 7 dots around it. All right, so now this is kind of hinting to us what's going to happen. And we can kind of look at the reaction to, again, right, what it would look like in real time. And so we have our sodium metal. We can imagine it giving up an electron and giving it to chlorine, right? So then we have our chlorine gas here. And the chlorine gas you can generate in situ, right, similarly to how you could accidentally release it with some cleaning products. So don't want to do that, but if you contain it, then you have some chlorine gas, mix those together. And so this is where our little cartoon can kind of help us, because, okay, our sodium is literally going to give this electron to chlorine here. And then we can see kind of the after effects, right? How do we get our cation and anion? And so that leaves sodium. And now we want to put a plus sign on there. So I'm leaving off the electrons. So of course, right, it does go back to the noble gas configuration. We could write its new electron configuration as just neon. But we normally don't, write those 8 dots around there. We just put a plus type to show that, yes, it lost its electron. And then we see, okay, this is how we make our anion. So remember, right, cation's positive. Got the T in the middle, there's your plus sign. And then we made our anion, which is negative. And for this one, I'll write its new electron configuration, so 3s2, 3p6. So 8 electrons around it. And then we want to write a negative charge on there to show that right now we're making chloride with 8 electrons. So that's good. And again, right, kind of a little bit of electronic bookkeeping too at this point. So we're seeing, right, our 1-to-1 ratio, how our 1 sodium gave up an electron to chloride. And so that's just what's represented down here. So again, we're trying to use our Lewis dot symbols, and they are honestly pretty powerful because they're going to help us in covalent bonding as well, but using to really see, okay, where is that electron coming from and why is it reacting in such a way. And again, we can see that with potassium, pretty similar, right? Again, we have our valence electron. We can now appreciate that potassium is in our group 1 alkali metals. And then again, we're going to appreciate the oxidation states. So it's 1 plus oxidation state. So that's something that we want to, if you don't have that, again, clearly indicated on your periodic table, do so. So again, right, oxidation states should track with their group numbers. So our alkali metals, right, we kind of mentioned they always lose one electron. That goes with, again, their NS1 electron configuration. We said group 2 was always 2+, right? Again, NS2 with those 2 valence electrons. Then we skipped over to group 3, where, right, they tend to lose 3 valence electrons. Then we mentioned the switch. So this is where things can get weird, right? So carbon, we're either 4 away, so we could take away 4 electrons, right? 1, 2, 3, 4. We're back at helium. Or we could add 4 electrons. 1, 2, 3, 4. We're at neon. So that's the switch point. And then usually nitrogen becomes -3, or at least for the common oxidation state. Group 6 is always -2. That's pretty standard. Halogens are always -1. Again, right, they're just 1 away. And of course, this is 0 there. And then the periodic table I gave you should be kind of more detailed. It has more oxidation states. Some of those are formalities, like for covalent compounds, that's where the positive oxidation states occur. I think the most common ones tend to be at the bottom on yours, but don't quote me on that. So make sure you have the big ones. And so let's go back to our notes over here. And we want to point out some other ones that are important. So it has scandium and yttrium there, so just kind of emphasizing that they tend to be 3+. We should also draw in there zinc. So zinc is always 2+ for our purposes. And then for our purposes, silver is always 1+. So this really isn't true. Again, right, chemists, research, blah, blah, blah. But we always consider it in basic Gen Chem to always have a 1+ oxidation state. And then we'll get into some weird ones later, so I'll point them out, such as indium. So indium can be 1+ and 3+, which is strange. And then next to it, tin, we'll find can be 2+ or 4+. And then I think those are, oh, and lead. So lead can also be 2+ or 4+. But we'll kind of get in to these. So I'll highlight. So zinc. All right, so then let's look at our more properties of ionic compounds. And so now this starts to answer also why is it soluble in water. And so again, right, ionic compounds are composed of cations and anions. And I meant to grab it during the break. I didn't get a chance to. And so what we find is that they're soluble in water, again, because of their charges. And so we can, again, start to think about this. We'll get this like a billion times throughout the course. And so before I start drawing little oxygen and water heads, we have to at least understand that water is polar, and we can at least appreciate which side is polar. So we have this oxygen here with 2 pairs of electrons. And so we can write that this is a partial negative on this side. And then we mentioned that fluorine is very electronegative. So if you look at your periodic table, well, right next to it is oxygen. So oxygen is also extremely electronegative. And so again, it tends to pull electron density towards it, and that leaves with our hydrogens with this partial positive charge. And so then in solution, what happens is your water surrounds and nucleates it. So the negative side would be pointing towards the sodium. And then similarly, it would nucleate around the the chloride, sorry. Just having now the hydrogens point towards the chlorine side, right? Opposites attract. And so that's how it's able to solubilize it, at least from a basic understanding. I'll bring my models hopefully on Wednesday to class so you can kind of play with that and see it. And so again, right, we're gonna see this in lab too. And so if we have just a pile of salt, right, we don't have any movement, so we're not gonna get any electrical conductivity. Again, you'll test that out and verify that. But then in solution, again, thinking back to your body and making your arm move, well, now your solution provides movement, right? Because there's always movement in your liquid. And so now with them floating around in solution, that provides movement for our cation and anion, and now we can conduct electricity. All right, back to this, how do we make our formula unit? And so kind of the idea with these formula units, and again, why I had you mark this up, is we want to balance the charges. So far we've looked at pretty straightforward examples. So if we look at sodium and chlorine again, so sodium, again, it has a 1+ charge. Chlorine has a -1 charge. We want our formula unit to be neutral unless we're told otherwise. So again, right, 1-to-1 ratio there. So that's what that is stating. So eventually we're going to get into these what are called polyatomic ions. I just didn't bring the polyatomic sheet today, but probably on Wednesday I'll bring that. But again, same thing. I don't want you to be kind of intimidated by this. So if we look, we can start breaking it down over here. So we have Al and then the CO3 thing. And so later you will learn that this CO3 is carbonate. It has a -2 charge. And again, all we're doing is balancing it out. So even though it has this more complicated structure, you focus on the -2 charge. You can look at aluminum, +3, and then we got our formula unit. So we'll get to how we got there more mathematically, but we can see 3 times 2 is +6, -2 times 3, -6, so 0. And so that's always what we're trying to accomplish, is then just get our formula unit for ionic compounds. So again, it's just our smallest electrically neutral ratio. Again, we'll practice that. All right, so now let's get into kind of the more details of that. And so the problem is we have to make a distinction between these two types of ionic compounds. And so we have what are called just our monovalent metals. So basically our metals that only form one type of ion. So these are typically going to be, right, group 1 and 2. I'll put 3 in parentheses. And then anything else that we've defined to be standard. So it mentions there's zinc. So again, right, maybe highlight zinc if you need to. Aluminum and silver. And also if you want like multiple copies of the periodic table, let me know in case it's getting messy. And then we'll come back to this one. So then we'll have to compare it to our transition metals and the weird ones I mentioned, but we'll come back to that. So let's look at our first example. So our group 1 and 2 are monovalent ones. And so to name them, it's pretty straightforward. So we can just name our cation. So we just state it, and we'll do like this one together. So we have sodium, and then we do our anion ending, but then we change it to "ide." So then, right, instead of chlorine, it becomes sodium chloride to show that it is an anion. All right, so take a minute or two. So what would be the formula for these next 3 examples? So just write it down and then we'll go over it. So what do we get for MgO? Magnesium oxide. Looks good there. What about CaF2? Perfect. Calcium fluoride. And then the last one? So just aluminum oxide. So save prefixes. All right, so that looks good. And so again, this one is trying to help you. I don't know if this periodic table is the most helpful. It's trying to emphasize that, like, oh yeah, these are multiple oxidation states, but honestly, it's not that clear. So I would say multivalent metals. Again, right, that makes sense for the transition metals. Just highlighting out these. All right, so now let's look at our multivalent metals. So now we're saying that they have multiple charges, aka multiple cations or oxidation states. And so all this means is that we have to put it in their name. And so for instance, if we look at iron, and again, right, not extensive, so it only lists iron 2 and 3. Again, you can have many other oxidation states that exist. Iron 1 exists, although rarely. So again, that's why you have to name it. And so we have FeSO4 and then Fe2SO43. So we have to be able to make the distinction between these two iron sulfates. And so we would write it. So we can say this is iron 2 sulfate. And so notice, and now we're using a much easier naming convention as we just write the oxidation state in parentheses using Roman numerals. And then so for this one, now we have iron 3 sulfate to make our distinction here between the two compounds. And so then, like I was pointing out earlier, we also have some strange exceptions in our P block, and so that's going to be lead, thallium, and tin. At least those are and indium. And so thallium is another 1 plus 3 plus usually. And again, the lead and the tin are 2 and 4 typically. And so again, we can use parentheses, makes it easier. So copper 2 means copper 2 plus, copper 1 plus. Again, different formulas, so now we can have copper 1 oxide versus copper 2 oxide with different formulas. So pretty similar, right, naming structure. So we still name our cation. We're just adding our charge in Roman numerals and then again changing the ending to "-ide". And so this is kind of fun fact / historical / in case you see it while digging around with old bottles of chemicals, you won't be totally confused. And so even back in the day when I learned it, we had to go by this older naming convention. And you can already kind of see maybe some of the problems with it. So the old naming convention is you have kind of the most common oxidation states listed. And then the lower one gets this "-ose" ending, the higher one gets the "-ic". Again, right, the limitation with that is I just mentioned that you could have iron 1 potentially, right? What if you have something weird, iron 4? That'd be difficult to make that distinction. So it doesn't necessarily always work out that well. Again, more common naming. So that's where it comes from if you see it. So, right, you could reference it, look it up, but mainly everyone's moving to this newer naming convention anyways, and that's much simpler and it works better because again, right now you can list anything here for the Roman numeral, any appropriate oxidation state. All right, so try to name these. So kind of pay attention what it would have to be, right, to make it neutral. Over there. All right, let's see how we're doing on this one. So what do we get for the first one here? FeCl2.
iron 2 chloride.
Perfect. So iron 2 chloride. And so these start to get a little tricky potentially, right? So we have to look at the oxidation state of chlorine. So it's typically -1, and then, right, maybe do a little algebra in your head. So you know you have the overall charge is 0, -1 times 2, so you're at -2, and then plus our x, right? Because we're trying to find our charge, and we only have one of those. So that's how we get 2. So right, -2, so we have to balance it with a +2. We're starting to get into maybe a little, I would call it reverse swap trick or swap trick. And so kind of the swap trick is how to solve this algebra quickly. And so you can go both ways with it. Usually I like to go converting name to formula. So what I mean by that is, okay, we have iron 2 chloride. So that means iron 2, 2 plus oxidation state, chlorine, -1. And so to solve the algebra, right, we have kind of two variables of x and y. The easiest thing is to bring the numbers down and get this swap trick. So now we get FeCl2 back out. But we can also kind of go reverse swap trick. And again, right, we back out the coefficients and we get our 2 plus and -1 back out again. So that kind of helps kind of check and double check ourselves. So what do we get for iron, FeCl3? So iron 3 chloride, looking good here. So right now 3 chlorines, so -1 times 3, so that gives us -3. So that's how we know we need a +3. Again, you could also now think about doing reverse swap trick. What do we get for SNO2? So double check that one. Well, I'm glad you said tin 2 though, because this is one of those ones that can trick us. And so let's kind of see how you got maybe tin 2, right? So if we do reverse swap trick, we have 2 plus, we have 1 minus. But let's check ourselves. So what's the oxidation state of oxygen though? Is it typically -1? So yeah, it's -2. So the swap trick hasn't necessarily failed us. We need to just go, okay, times 2. So that should leave us with 4 plus and -2. So it should actually be tin 4 oxide. But these get, like I said, they get weird because the swap trick fails us, right? And you can see why it fails us. We can review that. So tin 4 oxide will swap trick for oxygen 2. So then if we swap it, right, we get 2 and 4, but again, we want to simplify this, so that's why we get SNO2. So just kind of watch for stuff like that. So, right, this is a good example of we can still use our swap trick, just double check that what we're referencing, typically oxygen, matches. And again, that's your other hint, is like oxygen is almost always -2, so make sure that checks out. All right, what do we get for the last one then? CON? Good. Cobalt 3 nitride. And then just mental note, right? Nitride For some reason, the phosphides, nitrides, arsenides, I don't know, they tend to confuse people. I guess people forget about it. I don't know. I don't know what it is, but I've noticed those give people issues.
So what's the difference when these elements they end with IUD and ADE? The nitrate, the nitride, what's the difference?
Oh, 8, so those are polyatomics. That's why
Okay.
we're not there yet. So just focusing on the ide. So the ide is literally just the element, yeah, because you're getting into polyatomics,
Yeah.
which we'll just use a sheet to kind of reference those. But yeah, so nitride with the D though is just element. All right, so that does lead us into kind of our next section. Like I said, I didn't bring the polyatomic cheat sheet today for you. So basically, on Wednesday, I'll hand out this sheet. And so now we can appreciate some of what you were asking about. So let's look at some of our other ones. And so again, right, you're going to be encouraged to use this sheet in other classes, like a year-long course of this, right? You might be expected to memorize it, but we don't necessarily have time for that. I'm just going to point out some typical ones that we'll see, so you want to at least kind of familiarize yourself. So you eventually will have them memorized just by use. So hydroxide, this is one that we see a lot. We'll probably see it in lab. You know, we have NaOH, so that's sodium hydroxide. And again, notice with the naming, now we just name our metal, and then we name our polyatomic. So again, right, we have to have a polyatomic with a name. So you're not going to get like a random polyatomic. This is one of the few peroxides, this is one of the few exceptions to oxygen being a -2 oxidation state. So I just got finished saying that oxygen is always -2. Peroxide is the only exception. Peroxide is anything that looks like this, where R can be any organic, and the most basic peroxide is this, so hydrogen peroxide, you know, the little thing that you probably disinfect your cuts with. And then oxygen has a -1 oxidation state here. So only exception. Otherwise, oxygen is always -2. And then, so then we have carbonate, so that's pretty common, the CO3 with the -2 charge. We probably won't see sulfite. You will see sulfate, so SO4 2-. Acetate is always a tricky one because it's written in different ways depending on who's writing it. So it's just something you have to kind of learn. So we have C2H3O2, or sometimes you see this CHO thing. And so don't forget that this is also vinegar, acetic acid, so you will see it. Nitrate, so again, nitrate's pretty common. We have a lot of nitrate salts. Perchlorates are explosive. Probably we won't see too many chlorides, hopefully. Phosphate, so PO4 3-. So again, pretty common one. And then, so notice most of these are anions, right? So they're all negatively charged, except for the odd ones down here. So we have ammonium. So this is a cation, so NH4+. And then it throws mercury in here. I don't know that I would necessarily put it in here or not. It's not really a true polyatomic, but you can at least appreciate mercury in this 1+ oxidation state. All right, so see if you can try this. So maybe copy the problems down and then I'll scroll back up so you can have your polyatomic reference sheet. All right, so now if you need me to go back to the problems or I can zoom in somewhere. So let's see how we're doing with this one. So did we find this CR207? So what was that?
Potassium, chromium 6 oxide.
So did you find the CR207? So what is that called?
Pardon?
So what's that called? Like what's its name on the chart?
Chromium.
So we want to look at our polyatomic chart though, right? So that's why. Yeah, so it should be potassium dichromate, right? And so just name our cation like before, so potassium. And then, again, that's why I'll hand you this sheet on Wednesday. So then we have to look up, okay, the CR207, it has this -2 charge, and it's called dichromate. So excellent, potassium dichromate. And so then, did we find what this OH was? Did we name it? So I got a magnesium hydroxide. Does that sound good to people? Excellent. And again, right, we could get our formula back out. We know magnesium is always the 2+ oxidation state. You look up hydroxide, right, it's -1. Do our swap trick, and we get back out MgOH2. So, right, still balancing charges. Nothing's changed. And then what do we get for this one? Don't let the iron, don't forget about it. Iron 3 nitrate, perfect. So iron, and our Roman numerals, and now nitrate, NO3. Again, find it on our chart. So NO3 with a -1 charge. And there were 3 of them. So again, kind of reverse swap trick as well. Gives you iron 3 there. Questions on those? Kind of feel okay, maybe? So we'll keep practicing. So this is the sheet that I'll actually hand you guys. I have a copy here in my notes. So you can reference that. The notes should be going. Yes. So double check the sharing link. I don't know why it doesn't look like it's updated. Oh, it says it's up to date. So yeah, it's here. Otherwise, like I said, I'll bring a hard copy for Wednesday for everybody. So more. This one I think has a few extras, like organic ones like oxalate and tartrate. So you might see these in like supplements if you've ever, I don't know if people are into supplements, but yeah, so you might see these right as salts. So now you're starting to hopefully put context to all those crazy chemical names on the back of things. But yeah, probably a good place to stop. So we'll pick up, like I said, we'll do some more practice on Wednesday then. So just trying to hone this in, going over some practice problems. And then we'll look at a few other funny naming things, like our aqua complexes and acids. So we'll finish that up on Wednesday. Again, don't forget lab, don't forget your cotton clothing and pants, of course. And then a little behind on grading, but I do want to hand back your quiz at least, so that's in there. And then, yeah, any homework you could turn in. Otherwise, I'll see y'all Wednesday. And then if you have questions, though, feel free to stick around. Ask anything if you need. Otherwise, I'll see you Wednesday in lab.